welcome everybody to longitudinal data analysis using R. My name is Stephen Vaisey. I'm professor of sociology and political science at Duke University, and I will be your instructor for the next 4 days. I've taught this class many times, and it's usually a lot of fun. So glad you'll be accompanying me on this journey for the next 4 days. A few items of business before we get started. Okay, so as far as downloads and stuff, if you look here, this is going to give you, if you look, I'll show you. If you look here, you can see roughly the kind of thing that I asked you to download. Yours might not look exactly the same as mine from the Google Drive, and you can see a lot of different things in here. Probably the most important one for now is in the slides folder. There's a PDF version of the slides, but there's also an HTML version of the slides, which is how I render them in HTML using, I think I used Sharingan for this. This was in the pre-Quarto days, which is what I use now, just a few years ago. So you can see what's going on here. If you look inside this file right here, I just want to show you one thing. That'll be a good tip. If you look, if we open up RStudio here, and you open up this project, you can see here that there's a RMD file, a markdown file, which has all of the content, all the code for the entire class. So I got to install a few more packages because I just updated my R. But if we go ahead and look here, you can see everything is right here. So there's nothing cut and paste cut in this in these slides. So everything is just done from Markdown. And so that means if there's ever anything on the slides that you're looking at, so I can show you here, if there's ever anything on the slides you're looking at. So let's say, you're like, oh, what did he do, here? It always pays to visualize the data, and then you can see this distribution. One of the things you can do is take a look here in my eldar-slides.rmd, and you can just sort of look for it always pays to visualize the data. And you can see here, like here's the code for that slide. So if you're interested in seeing the code for that, I will often show you the code, but if there are situations where I don't, then you can see it there. So that's just a tip to follow along. I think that's it in terms of business. So we're going to just go ahead and dive into the material here. And if anybody has any questions along the way, you can, of course, you can ask. Okay. All right. So this is not really, we're not going to go over this right now. This is just all the packages that you will need. And we're not going to need this for this first session. The first session is mostly going to be conceptual. So we're going to mostly focus on just getting that key ideas out for this for the course. So we really won't need you to code that much or at all in the first 2 hours here. But if you want to make sure that you have everything that you need installed, this is some good code to copy and paste. I also put this on the README in the on the Google Drive. Okay, so we're going to start with the big picture. Okay, what is longitudinal data? Okay, longitudinal data is repeated measures of the same units over time. And so individuals measured several times is by far the most common scenario, at least in the kind of research that I do. But it could be any entity. It could be states, could be firms, could be anything that can be measured repeatedly. It could be classrooms, could be hospitals, could be anything. So in general, I just want to point out the methods that we're going to cover in the next 4 days are designed for situations where we have many more units than we have time periods. Now, this is like an imperfect way of carving this up. But the contrast I'm trying to draw with here is with like time series methods in econometrics. So let's say you have like the daily stock price every day for like 3 years. That's going to require a slightly different set of tools than the kind of tools that we're going to focus on here. The idea is still generalized, but we're not going to focus too much on that like very intensive single unit longitudinal case that economists would call time series data. We're not going to focus on that here. We're generally going to focus on situations where we have, let's say 1,000 people measured 4 times or 500 people measured 7 times or something like that. And so that's going to, the kinds of situations that we're going to deal with are going to tend to be situations where the number of respondents we have is much more than the number of time periods we have. A lot of the ideas that we're going to work on in this course do not require that. So, this is like kind of a fuzzy category, but in general, this is the kind of situation the methods we're going to use are designed for. Okay. So the bottom line is there are really 2 things you can do with longitudinal or panel data. The first is you can model the trajectory of an outcome in groups or individuals over time. So you can think to yourself, like, okay, like how do the wages of people with and without college degrees diverge over time, for example? That's one of the examples we'll look at. or how do the sort of symptom progression differ between men and women with this particular disease. So we can use longitudinal data to model the trajectory of an outcome in groups or in individuals over time. So that's one thing that we're going to work on, one situation we're going to work on. The other situation is that we can use repeated measures to make better causal inference. And I'm gonna show you that. This is going to require a situation where people are essentially move in and out of treatment states. And so a situation where, some at a certain period of time, the person's not treated, at a later period of time, they are treated. That will enable us observing people in both those states. And we're going to talk much more about this later, but observing people in both those states is going to enable us to essentially control for things that are not in the data. That's going to be the ultimate goal. So there's always a little bit of tension here between these sort of two objectives, and much of it is going to depend on the specific character of your data. So if somebody tells me, for example, oh, I've got 7 waves of data, 1,000 people, like that's not nearly enough information to make a judgment, for example, about what kind of model you should use. It's going to depend on the time varying status of the treatment. It's going to depend on how often it varies. There are a lot of things like that. So we're going to focus on all these things here, but I wanted to point out these are the sort of two main things that we can do with longitudinal data. We can model trajectories, and we can essentially control for, in some cases at least, unobserved heterogeneity, meaning unobserved confounding, confounders that we don't have in the data set. So those are the two things that we're gonna focus on in this course. The two big things we'll focus on in the course. Okay, so an important meta point here is about the relationship between data and research questions. Now I'll tell you, like before I started telling people this, I have this slide is relatively new, only a few years old, but I've been teaching this course and other courses like it for a long time. And one of the most common questions I would get from people would be something like, this is what my data set looks like. What kind of model should I run? That's an extremely common question that I would get. And that is a question that honestly is impossible to answer. The structure of your data determines the set of possible models you could run. And there are always so many possible models that you could estimate. It's really your research question that determines, within the scope of what your data will allow, what you should do. And a lot of times people think, oh, if I have students nested in classrooms, nested in schools, that means I should do a 3-level, multi-level model. No, that doesn't follow. It depends on what the question is. It totally depends on what the question is. So one of the things we're going to emphasize a lot in this course is the dependency of the model on the research question. And so at many times in this course, we're going to sort of pretend that we have research questions. We're going to pretend that we have, oh, this is the thing we're interested in. If we were interested in this, this is what we do. If we were interested in that, this is what we do. So this is a really important thing to keep in mind. And this will also be useful for you when you're asking me questions on the Slack. So if you're asking me questions about your own situation on the Slack, it's always good to tell me what you actually want to know. And the heuristic I use with my students for this is, if you had no ethical constraints, no resource constraints, no constraints of any kind, and you could just experiment on the world however you wanted, the way to figure out what your research question is to determine what experiment you would actually conduct. This is a heuristic. What experiment would you conduct if there were no ethical considerations, no resource considerations? This essentially wasn't real. You were just going to go ahead and do this whatever experiment you want to do. That would be a way to sort of figure out what a research question is, because people are actually really good. And I've been teaching, working with PhD students for many years. People are really good at knowing what their research topic is. Like knowing what your research question is like a totally different level of precision. And so like the journey from research topic to research question is actually a really difficult one. And so that's one of the reasons why I try to help people understand, like if you could do this experiment, if there was an experiment you could do that again, no resource constraints, no ethical constraints, like what would you do? And, and this leads to some interesting conversations in class where people basically tell me about, handing people babies and, giving people babies and forcing people to get divorced and all these sorts of things. But that's really what you want to know in many cases. And so it's important to think about that. Okay. So especially when you're asking me questions on the Slack, I want you to think about like, what do I actually want to know? Okay, what do I actually want to know? And one answer, a non-allowable question to there is like, I want to know what all these 12 variables do to the outcome. That is not a research question. Sometimes people try to slip that past me, but that will not work. Okay, that will not work. Okay, all right. So the question is, what do we want to know? So what's the kind of thing that we want to know when we approach data analysis, but in this case, with a specific focus on longitudinal data analysis. Okay, so I'm going to assume in this course that you are interested in estimating a quote unquote treatment effect of some kind. And that is, you want to know how some independent variable, some X variable, some observed, predictor causally affects the outcome. So I get it that we've all learned this, is associated with. We've learned this sort of weaselly language of antecedents and consequence and, all these sorts of things to try and avoid using causal language. Many of us, depending on our field, will have learned that. But ultimately, the thing we want to learn, the thing we want to know is how does this thing affect the outcome? How does this thing affect the outcome? So this is really hard to do. It's really hard to do, but it's really important to know that's what you want to do and to really think, okay, what assumptions do I have to make for this to be true? What kind of thing do I actually want to know? And so I'm going to assume in this course that, like most people, you want to estimate the effect of some X on some Y, some X on some outcome. And so this language of treatment, it will be familiar to many of you, but it will not necessarily be familiar to all of you. That language evokes like medical treatments and experiments and treatment and control and things like that. But these days, this idea is used much more broadly. So we could talk about like the treatment effect of a college degree, which is obviously not randomly assigned. We could talk about the treatment effect of having, a proportion of your network be involved in, in the use of methamphetamine or something. Like these are treatments that no one randomly assigns, but we can still think about them as treatments. That's the way that the language of causal inference has evolved, to think about, when we want to know what some X does to some Y, we want to think about that as a treatment effect. And there are many different kinds of treatment effects. We'll talk about a couple in this class, but there are many different kinds of treatment effects that we can be interested in estimating. One paper that's very accessible, that's useful in this domain, is this Lundberg et al. Paper, What is Your Estimand? Defining the Target Quantity Connects Statistical Evidence to Theory, from the American Sociological Review. Came out a few years ago. This is a really good paper for helping you think about, what do you actually want to know in your research? So if you want to sort of take this, your sort of reflection on what you're working on to a different level, this kind of exercise that comes out of an engagement with this paper is a really useful exercise that I use with my my PhD students quite a bit. Okay. So the simplest treatment effect to understand is what's called the average treatment effect, or ATE, sometimes this is called. And this is an estimate of the average causal difference the treatment would make to an outcome for a member of the target population. And so I want you to think about a subtle difference here. We might think about, okay, what is the monthly earnings difference between people with and without a college degree in the United States, for example? We might want to know, okay, what is the average difference? That is not a causal question. That's just descriptive. That's like what are the average earnings of somebody with a college degree? What are the average earnings of somebody without a college degree? The difference between those two is just the difference. Okay. But let's say you want to know, well, how much is the average difference because of the college degree? Meaning, if we could randomly assign it, like let's say age 22, this is a little harder thought experiment to do because the treatment takes 4 years to get. But let's say, at age 18, we took all the people who were about to get a college degree and we assigned them somehow not to get one. And we took all the people that were not going to get one and we somehow assigned them to get one. What would the difference look like in that case? Like, what if we could switch everybody's treatment status? Or to make it even simpler, what if we could take one person and just change their treatment status? On average, what would we expect the difference to be? And so this is the question of how much more do college graduates make than non-college graduates because of their degree. And so we can see this kind of language all the time. Like, so if you remember, I mean, many of you will remember this, of course, but like during COVID, people would say things like, oh, 80% of people who went on ventilators died. So ventilators are killing people. 80% of people who went on ventilators died. Now, the idea is not like to compare the average life expectancy of someone who's on a ventilator to the average life expectancy of someone who's not on a ventilator. That's not how you would answer the causal question of like, do ventilators work to keep people alive? What you would want to do is say, well, okay, let's take a person who's on the ventilator, and then what would have happened if I had taken them off? That'll lead us to another kind of treatment effect we'll talk about in a minute, which is the average treatment effect on the treated. But the idea here is that there's a difference between the descriptive categories and the causal effect. So we just say, hey, what is the average difference between these two groups? Fine. But then you might want to say, well, what is the average difference between these two groups because of their difference in treatment status? People are not randomly assigned to be on a ventilator. People are not randomly assigned to a college degree. People are not randomly assigned to have babies. They're not randomly assigned to, to residential mobility. They're not randomly assigned to go to prison. They're not randomly assigned to do, lots of things. So people are selecting into treatments, or other things are selecting them into treatments. And so that makes these questions much trickier. Okay. So the ATE, just to be a little bit more precise about what we're talking about here, the average treatment effect, the average treatment, the unconditional, sometimes it's called the unconditional average treatment effect, because it means what's the average treatment effect for anyone in the population, is defined in the following way. So let's say we want to know, we'll pretend we have a research question here. We want to know what is the relationship, or what is the causal effect of having a unionized contract on wages. So the idea being like, hey, if we can get people unionized, they'll earn more money. So we want to see if we wanted to answer that question, we would need to know what is the actual effect of unionization on wages. We don't just want to know what do people with a college with what do people who belong to unions earn? What do people who are not in unionized jobs earn? That is a very different question. What we want to know is how much, if I took a person now who's currently not unionized and I put them in a unionized job, what would we expect to happen to their wages? Or similarly, what if we took a person who was currently in a unionized job and we took away their union status? What would that do to their wages? Okay, so these are causal questions. So one way to write this out is right here. Now, don't get freaked out by equations and stuff. We're gonna go slow. We're gonna look at some equations in this course, but we're not going to be deriving anything crazy. This essentially just means average. So what we want to know here is the average the average difference between these two variables. And these are like kind of special variables. These are, if you've taken a course on causal inference, or you've done some reading about causal inference, you may recognize this notation as related to the potential outcomes framework. But if you haven't, let's go through this together. So this variable right here, so y is just wages. It's just a variable. You're used to this. Y is wages. How much do you earn per month, let's say? How much you earn per month? That's easy. Okay. Now this little thing right here, y1 or y superscript 1 here, means one of two things. It basically means if you belong to a union, it means how much money do you earn? Because a 1 here indexes treatment status. 1 means treatment, and 0 means control, if you want to think of it that way, or untreated. And so the idea here is that y1 superscript 1 here, yi superscript 1 is either a person's wages if they belong to a union. So if they're treated, this is their actual wages. So if I belong to a union, my value of y1 is how much do I actually earn? That's it. Simple. Or if I don't belong to a union, what y1 means is what would my wages be if I did belong to a union? So this essentially is, imagine a world where I belong to a union. And maybe that's the real world, so we don't have to imagine. Imagine a world where I belong to a union. How much money do I make? Okay, that's the idea. And we want to compare that to another world, another counterfactual world, maybe, where it is, how much do I earn if I'm not in a union? Like, how much do I earn if I'm not in a union? And so the difference between these two quantities is the average treatment effect. It's basically the difference for each person. So think about it this way. It's for each person. How big is the difference between the world where it's still me and I'm in a union, or it's still me and I'm not? So this is a within person quantity. So this is a counterfactual within person quantity. So what does it mean to be counterfactual? It means that for any individual person, you either belong to a union or you don't. Okay. And so one of those things will be factual, real, and one of those things will not be. And so what we want to know is the difference for each person between those two states. Now you might ask yourself, wait, how could I possibly know this? Like, one of these is just imaginary, one of them is imaginary. So a lot of the techniques we're going to look at in this course are going to be focused on trying to estimate that counterfactual quantity. We want to know, for example, like, what would this group look like if they hadn't received the treatment? And if you are interested in grammar, you can look here and see, when you start to see language like this conditional kind of language, what personized wages would be if they did belong to a union. This is conditional tense. And whenever you see conditional tense like this, or often past conditional tense, that will tell you that you are seeing somebody talk about a counterfactual. like how much longer would I have lived without a kidney transplant? You know what I mean? That's counterfactual language. How much money would I currently be earning if I hadn't completed a PhD? You know what I mean? These are counterfactuals because they're not real. Okay, so that's the idea. And historians do this kind of stuff all the time. Like, what would the 20th century have looked like, if the Allies hadn't imposed such harsh economic restrictions on Germany after World War One? You know what I mean? Like, we don't know, but this is the kind of thing historians like to talk about. And so their counterfactual history, or you can think about this in fiction all the time, where people talk about like what if the Axis had won World War II? That's like what is that? Man in the High Castle. There are a lot of these, or like there's a show on Amazon For All Mankind, which is like what if the Soviets had won the space race, for example, the race to the moon. You know what I mean? So people are fascinated by counterfactual history. And counterfactuals are really important in statistics as well. When we're interested in causal inference, we want to know like how different is the world we actually live in from a hypothetical world where the treatment we're interested in didn't happen or did happen. So that's the kind of information that we want to know. And as we're going to see in this class, longitudinal data analysis is going to help us in many cases, not all cases, but in many cases, it's going to help us get closer to that. Okay. All right. So that's how that language, that counterfactual, that past conditional language is actually really useful for identifying the kind of things that we want to know. Okay. So the ATE here is just the average difference between these two states. Like, hey, what if everybody, so you can think about this as what if everybody switched? What if the people with a college degree or whatever? What if people in union stopped being in a union? What if people who were not in union started being in a union? You can think about the average difference between those two. That's called an unconditional average treatment effect. Just means basically close your eyes, grab somebody at random, whatever they are, turn them into the opposite, and what's the average difference that makes? So the ATE is really simple to understand. It's just whatever you are, imagine you were the opposite and take the average difference it makes to everybody in a population. Sometimes the ATE doesn't make sense because, the treatment that we have doesn't make sense to apply to like a random person in the population. So like it doesn't make sense for all adults in a society, including say teachers and engineers, to participate in a government job training program that's intended for low-income workers. And so if it's like, oh, we'll just take a random person from the US labor market and put them in this job training program, to the average person, that might actually decrease their earnings. We don't know. It'd be like, I mean, a sort of more obvious and gruesome example of this is if you want to know what the effect is of a kidney transplant on people, you don't say like, well, I'm just going to grab random people and start giving them kidney transplants, you know what I mean? And see what happens. Like that's going to reduce their life expectancy. That's going to reduce their life expectancy. So sometimes we have a much more targeted population in mind. And one way to think about that targeted population, especially in a clinical setting, but not exclusively in a clinical setting, is to define this treatment effect as the average treatment effect on the treated, meaning what does this treatment do to the people who receive it? So this is a world where people actually are receiving the treatment. Some people actually do get college degrees. Some people actually do get kidney transplants. Some people do actually participate in job training programs. Like these things actually happen. Some people do participate in new reading programs. Some people do there's people experimenting on and themselves and each other all the time. So in this case, what we're interested in would be something like the average treatment effect on the treated. And so that's the difference that the treatment made to the people who received it. And so that means in the real world, all these people actually receive the treatment. Okay, in the real world, all these people actually receive the treatment. So the ATT again is going to be, again, this quantity, right? This is the average. This means average. We're going to take the average value of what your actual outcome is. Like, hey, you received the treatment. You got the kidney transplant. How long did you live? And what we want to know is, hey, how long would you have lived if you hadn't received it, which is what the 0 means. So we want to understand how the difference between what actually happened and what would have happened to people who received the treatment. And the reason that we care about this difference between the ATT and the ATE is because an ATT says, look, the people who are receiving the treatment received it for a reason. And what we want to know is how much worse off, in many cases, would they be if they hadn't received it? And so it's a more targeted question. It's a more targeted question. And as you'll see later, this is the kind of thing that we often people do in cross-sectional data using things like propensity score matching, propensity score weighting, covariate balancing, propensity scores, things like that. And the idea is, we're going to compare a group of people who receive the treatment to another sort of similar group who look like them in every other way that's observable, except they didn't receive the treatment. And so we're going to do one better than that. In fact, there's a tight correspondence conceptually between panel data methods and something like propensity score matching, because essentially we're going to compare you to somebody, not only to somebody who like kind of looks like you, we're going to compare you to you. And that's even better. We're going to compare you to yourself because you are very much like you in many ways. And so we're going to do that over time, especially in situations where treatment effects are time varying, like where we can observe people in multiple treatment states at different times in their life course. So that's the thing we're going to think about as well. Okay. So these are ideas. And so this is the kind of thing where if we think about these issues, we don't have to become like experts on them. But when we think about these issues, they can help us gain clarity on the kinds of things we actually want to know. And so as you're thinking about your own research, I want you to, spend some time. It pays off to spend some time thinking about like, well, if I could do an experiment, what would I do? What do I actually want to know? If I wanted to intervene on the world in some way, how would I do it? And again, with the full understanding that, like in many cases, a lot of the stuff that we're interested in, I look at stuff like aging and like belief change and things like that. In my case, I can't make people like age faster or stop aging. I mean, like it doesn't make sense to think about intervening on people's like aging process in terms of time. That doesn't make any sense. But you can think about even things that you couldn't manipulate in these terms. It just helps you get your ideas clear. So we're going to be returning to these ideas as we go through the class because they're going to be really important. But I wanted to give you a little bit of a crash course on some of these ideas. Okay. So this topic, like I said, is complicated. We're not going to go too much deeper on this, but it should provide a background for what we're actually trying to do, which is to estimate the effect that some cause has on some outcome for some population using panel data. And so it's not just like, oh, I want to see how all these X's, predict this Y. I mean, that's perfectly fine to do if you just want prediction. But most of the time, the real value added of panel data is going to mean try to help us get better causal estimates. So we're going to focus on that when we can. You're going to see we can't always do that, but we're going to see how far we can get. Okay. All right. So here's a little summary of what we can do with panel data. And a lot of it depends on the status of X. So if we look at this first column here, the first question is, can Y change? Can the outcome actually change over time? So if I measure you 7 times, and let's say I measure you 7 times and I say like, what color are your eyes? 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 That doesn't really change. And so like if my outcome variable doesn't change, then it's not really panel data. In panel data, we always want to, we're almost always, and I would go so far as to say always, except there's always an exception. But I would say basically always about outcome variables that can change. So your outcome variable can always change. Okay, so the real important question is going to be, can X change? Can the X that I care about, can it change? Okay, so you can think about situations where, so let me give you an example. Let's say I have a long study, like a 10-week study. I'm going to assign half of the people to some treatment. I'm going to assign half of the people to some control. And I want to see how their outcomes evolve over time. We're going to actually look at an example like this later in the course. In that situation, the whole 10 weeks that we observe people, you're either in the treatment case, you're either in the treatment group or the control group. So X, in that case, X cannot change. You're assigned to a treatment group or the control group, and that's it. The same thing with something that is not assigned in the same way, but let's say something like biological sex doesn't change, over the course of a study. If we observe people over like a 5-year period, whether they're male or female will be consistent. I know it's a little more complicated than that, but it will generally speaking be consistent. And so this is where a treatment, if we want to estimate like how some outcomes evolve that are differently between male and female respondents, like the X, the treatment, if you want to think of it that way, does not change over that period of time. And when we're in that situation, the options we really have for panel data is to use it to model trajectories. That means we're going to say, hey, how do these two groups converge, diverge, maybe converge, then diverge, or whatever over time? So our question is going to be about that. Okay. Now, if X can change, like meaning, hey, like let's think of some treatments that can change. For example, are you exercising regularly or not? Let's say I do a 5-year study, every 3 months, and I want to know like how much the person's been exercising lately. That could fluctuate quite a bit. A person could be exercising regularly at some time points and not exercising regularly at other time points. In a situation like that, we're sometimes observing the person exercising, we're sometimes not observing them exercising. So that's the situation where the X that we care about, the treatment effect that we care about, can be changing. Adherence to some kind of medication regime would be another thing like that. Belonging to a union, is your current job governed by a union contract? That could change over time. Are you currently living with your parents? That could be a thing that could change. Maybe sometimes yes, you are, and sometimes you're not. Do you have a child living with you at home? That could change over time too. There are tons of things that could change over time. And when we have that kind of situation where we observe some people at least in both treatment states at different time periods, we can still model trajectories if we want, but we also get this new opportunity here, which is to do better causal inference, because it gives us some tools, some data that enables us to compare people in different treatment states. And so these two situations are quite different, actually. These two situations are quite different. So when someone tells me like, oh, I have, this long study and, I have this many observations and I have this many waves of data and here's my outcome variable, like the most important thing for me to know generally in longitudinal data analysis is the treatment that you care about. Does it change? How often does it change? How many people for whom does it change? So let's say you're saying, oh, I want to study the effect of, the effect of like divorce on child outcomes. Okay. Let's say I want to do that. Like if I have a sample of children and only 5 of their parents go through a divorce over a period of like a year, let's say, yes, that changed, but not enough people changed to enable me to do this causal inference stuff because I just don't have enough people who actually went through that transition. So there's going to be all kinds of as you'll see when we get deeper into the subject, that power analysis or thinking about like, do I have the data to do this? We won't do too much on formal power analysis, but we'll talk about this in an informal way, which is that it doesn't always matter just what your N is. Like, oh, I've got 10,000 people. If you get 10,000 people and only 100 of them change treatment status, then you kind of only have 100 people. It's not quite that simple, but in a way you only do. So we're going to have to think about we're going to have to think about statistical power in a slightly different way in panel data. It's going to depend on how many people change. Okay. So that's an issue. That's an issue as well. Okay. Okay. So, all right, let's continue. All right. So again, I just want to reinforce this point because it's an extremely important point, and it's important not just for this class, but it's important for life, which is the structure of your data determines what you can do, but your research question determines what you should do. And if you think about your research question, I promise you it's going to be very painful. But once you actually figure out what your research question is, it's going to make your life so much easier. And again, that research question can change from paper to paper, analysis to analysis. You're not committing to like a lifetime single research question. But like if you actually want to answer a question, it really does pay to think about what question am I trying to answer right now? Rather than saying, oh, I want to know all the things that cause some people to make more money than others. It's like, oh, are you really prepared to talk about like, you know, genetics and height and attractiveness and parent background and college degree education, network effect? Are you really prepared to talk about all those things? Like that, like that's a much harder question to say, like, why do some people earn more money than others? That's a very tough question. That's a very tough question. But to say something like, well, what would happen if I assigned people to a job training program? Like, how much would that help? You know? That's a much easier question to answer than like, why do some people earn more money than others? That's a very, very tough question to approach statistically. And if you're anything like me, when you were trained in statistics, that's kind of how you were trained, is to just think like, oh, I've got this Y and let me just put all the X's in there that might affect it. And then go through my table and be like, well, X1 does this, and X2 does this, and X3 does this, and X4 does this, and X5 does this. And that's what I learned. But people who think a lot about statistics, people who think a lot about statistics in the last 15 years or so, have really realized that's impossible. Like you can't get 12 like net effects out of a single regression model. Like you really need to think in a much more targeted way about like what kind of things you want to know from your model. So that's how we're going to approach this issue. And it will simplify things for you if you think about it in a sort of quasi-experimental way. Okay. All right. Okay, so panel data and practice. Okay, enough of the conceptual, the conceptual beginnings here. Let's talk about some practical issues related to panel data. Okay, the first one is that panel data comes in one of two forms. So it's generally long form, where each row is a unit observation, and most units will be represented by multiple rows. Okay, so it just means every single row is an observation. Some units might be measured 4 times, some units might be measured 5 times, some units might be measured 2 times, whatever it is. And so however many times you're observed, you're going to have that many rows. Okay, so that's one possibility. That's what's called long form data. We'll look at an example of this in a second. Wide form data is where each unit is represented in one row, and repeated measures are encoded in different columns, different variables. So let's take a look at 2 examples of this. So let's say we follow a sample of adult workers and we interview them once a year for 3 years. This is like a real data set, but it's simpler. Okay, we're going to use this data set later, but it's actually longer than this. But anyway, just keep it simple. So each time we do this interview, each time we interview them, we say, okay, how much money did you earn in the past year? That's a thing. We also say, well, how many weeks did you work in the past year? Like, how many of the 52 weeks did you actually work in the previous year? And then number 3, we might say to them, okay, how many years of education did you complete? And now here, number 3, let's say, and we're going to see this is the case in a real data set we're going to use, that we only ask them that the first time. So if it's a sample of adult workers, let's say age 25 plus, we ask them how much education they completed, but we only ask them one time. I want you to think for a minute about why we might only ask that at the first wave. Why might we only ask people, like, how many years of education did you complete at the first wave? Just take a moment. Okay, here's a possibility. The possibility is that basically it costs a lot of money to ask people research questions, survey questions. And so if you don't think that my sample of people who are 25 plus, only like a few of them are going to actually maybe complete a college degree after the study period or during the study period, or maybe some of them will complete a high school degree during the study period. If you think maybe only 1 to 2% of people are going to change, then you're actually going to cause more trouble for yourself, because people will misreport their education, and you'll spend a bunch of money collecting a survey question that you don't need an answer to, because you basically already have all the information you need. So this is one of these times where we're going to talk a lot about time constant variables in panel data. Variables that don't change over time. Many of those are like, actually, if you want to think about it this way, like ontologically time constant. Like, they really don't change. Like, what year were you born doesn't change. No matter how long you live, what year you were born will never change. So that's like a really time constant variable. Okay. Or like, what's your birthday? That will never change. Okay. How much, was your mother in the labor force at, when you were 16 years old? That doesn't change. Okay. That doesn't change. But some things are effectively time constant in a particular data set, because they're only asked the first time, for example, like, how much education have you completed? And so even though this could change, it actually is time constant. Okay. In that data set, it's time constant. So we need to be aware of the difference between things that are actually time constant and things that are sort of methodologically time constant, because we only have them measured once. Okay. But in this case, I just wanted to introduce you to that idea. So let's take a look at 2 variants of like 2. So we have 2 people, each measured 3 times. This is what long form data looks like. Okay. We're going to have 6 rows. So an ID number for person 1, person 2, right here. So person 1 at time 1, person 1 at time 2, person 1 at time 3. We have person 2 at time 1. We have person 2 at time 2. We have person 2 at time 3. And for those things, you can see, how much money, what is the log dollars that you earned this year? So if we exponentiate this will give us the amount of dollars that these people earned. This is log dollars. This is log dollars for person 2. This is log dollars for person 1. And then how many weeks did you work this year? So this person worked 32 weeks in the first year, 43 in the second, 40 in the third. You can see all this. But this is and then education. Now you'll notice here that this person has 9 years of education. This person has 11 years of education. And if you just looked at these two people, you wouldn't actually know, like, could they have changed? Like, did they just not change? Or like, were they never asked the question? And so it's always important to know, like, did was the person actually asked the question and said, no, everything stayed the same, or if they just weren't asked the question. In this case, we know how the data were collected. People were only asked at the first wave. And so that's the idea here. Okay. So this 9 years of education for this person, 11 years. Now you'll notice, however, that it is written down in each row. It is actually written in each row because this is like, what is this person's status at what is person one's status at time three? Well, they still have 9 years of education. What is person one's status at time two? They still have 9 years of education. This is methodological, though, because the person was never given an opportunity to update their answers, but we still need to record it in this way. Okay, we still need to record it in this way. So this is what's called long form data. So if we had 100 people, we could just, or 1,000 people, we could just keep going. Everybody gets 3 rows, and that's how the data are encoded. All right. Okay. Wide form data looks different. It's 1 row per person. And so we're going to have this person. Here's person one. Here's person one. They have 9 years of education. And you can see here that this is a time constant variable. It's much easier to see that this is a time constant variable because it only appears once in the data set. So here's person one. They have 9 years of education. And you can see now that time is now encoded in the variable names. Time is encoded in the variable name. So here's your log wage at time 1. Here's your log wage at time 2. Here's your log wage at time 3. Here's your weeks worked at time 1. Here's your weeks worked at time 2. Here's your weeks worked at time 3. See what I mean? So this is wide form. And so it's easier to see in this format that education is time constant because it doesn't have a suffix. And that will, and as you'll see later, that's going to be an important distinction. But no information is lost between these two. No information is lost between these two. Okay, we could take this and we could put it in this form and vice versa. There'll be no information is lost, but it's in a different shape. Now, both formats contain the same information. We're going to use long form for a couple of reasons. Number one, because all of the functions that we're going to use want it in long form. That's the main reason we're going to use it, is because all the commands we're going to use, all the functions we're going to use to estimate models want it in long form. That's the real reason. But also, long form data can store data more compactly in some situations. Like, for example, if we have unbalanced data. So if different units have different numbers of observations, like some people are observed once, twice, 4 times, 5 times, then we don't have all these empty cells, like, okay, what's time 1, time 2, time 3, time 4, time 5, and maybe a person was only measured at time 1 and then not for the next 4. We don't just have to have 4 blank spots for all the additional variables. We just can say, well, we can encode that person in 1 row. Missing data, if some whole observations are missing, like a person does not follow up, a person does not answer a follow-up survey, for example, missing data can do that. Or data that's unequally spaced, like I'm talking as if all longitudinal data is wave 1, wave 2, wave 3, wave 4, wave 5, but longitudinal data can sometimes be like, okay, what was the date you went to the doctor? And did you get this test? And so in that case, there's not a discrete times like wave 1, 2, 3, 4, 5. There's just how long has it been since you've been to the doctor? And so in a situation like that, wide form doesn't really make any sense because we can't say like, oh, we don't want a separate column for every single day of the year, most of which is just empty. So when we have any of these 3 situations, we want to have data in long form. Now, wide form was common because in many situations, wide form was common because it could store data a little bit more compactly in a balanced data case because your time constant variables weren't being repeated. But today, data is almost always distributed in long form because we don't have the same storage constraints that they had, for example, in the 1990s. So it's like, hey, it's okay if our storage mode is a little bit more inefficient because, computer hard drive space is very cheap. Like server space is very cheap. And so long form data is still very, very common. You will still encounter wide form data from time to time. We will talk a little bit about getting wide form data into long form data. But generally speaking, it's the kind of thing that you're going to have to look up most of the times you do it, because generally speaking, it's going to be something you'll do like once per project if you have to do it. And then the next time you'll do it, be like, how did I do that again? So I will definitely show you how to do it, but it's the kind of thing that you're not going to do enough to like memorize it, so we're going to do that. I'll show you the principles, and then it'll be the kind of thing where you'll do it and you'll be like, oh, okay, that wasn't so bad. But then the next time you have to do it, you'll be like, I can't remember what I did. And you'll have to learn it again. So, okay. So, we can reshape the data in a couple different ways. So in dplyr, you have pivot wider and pivot longer, which are useful ways that are built in sort of tidyverse ways to reshape data from wide form to long form. Now, what I would recommend is if you're doing a lot of stuff with panel data, if you're doing a lot of stuff with panel data, there's a package called PanelR, which I'm going to show you how to use. This is written by Jacob Long, who is he's a professor. I can't remember where he is right now, but he's written some really useful R packages that we're going to use a lot in this course. This package PanelR has widen panel and long panel, which are actually way easier to use than even pivot wider and pivot longer. And so I'm going to show you how to use those as well, which will enable you to really easily go back and forth between wide form and long form. Now, some people might want wide form data for structural equation modeling. That'd be the one contemporary situation where people would want wide form data is if they're doing SEM. So many of you will not be doing, in fact, most of you won't be doing SEM. We'll talk a little bit about SEM at the end of the course. But there are commands now that enable you to do SEM on long form data and stuff. So we're not going to spend too much time like directly on structural equation modeling. Okay. All right. So here is a data set, for example. This is one of the data sets we're going to use in this class. This is a data set about teen poverty. And you're going to see here, this data set is in wide form. So here is the person's, so this is glimpse. I don't know if many of you have seen this. So if you are, and so in tidyverse, there's a command called, or a function called glimpse, which essentially shows you the data kind of sideways. So it'll show you the column, it'll show you the column names here, and then it'll basically show you as many observations as it can. And the idea is just to kind of give you a glimpse of the data. So this is a little bit like head, of a data set, except it turns it sideways instead of putting it this way. Because if you've ever had this is 28 columns. If you do, head teen poverty, it's going to show you like the first 5 columns, and it's going to run out of room because it's not going to be able to show you that real estate to the right on your console. And so what Glimpse does is it shows it to you in sort of like it tips it on its side and shows you all the column names. And then you can see, as many of the observations as you can. So like here's person 22, here's person 75, here's person 92, here's person 96, here's person 141. And then what you have is, hey, was this person in poverty at wave 1? This person was, these people were not, this person was, etc. Did they have a baby at wave 1? Anyway, you can see all this. And you can see this is wide form because it's like I've got a person. Were they in poverty at wave 1? Did they have a baby at wave 1? Were they living with a spouse at wave 1? Were they in school at wave 1? How many hours a week did they work at wave 1? And then you can see all this information repeated. Here's what it was at wave 2. Here's what it was at wave 3. Here's what it was at wave 4. Now, I don't know why it's here, but you also have how old were they when they started the study. So you have to watch out, by the way, in panel data. We'll talk more about this later. You have to watch out in panel data. When you see variables like age, you have to know if this is wide form, it can't possibly be what is this person's age today, because it's not it's time constant. You notice we don't have age 1, age 2, age 3, age 4, age 5. We just have age. And so if age is a time constant variable, that must mean how old were you when the study started? Not like how old are you right now, because this variable is time. This variable is time constant. There is no age 1, age 2, age 3, age 4, age 5. There's just age. So that has to be a variable that's time constant. So this is one thing you want to watch out for. We're going to have some situations like age and some situations like work experience that are going to actually be obviously they change over time. Like age changes at the rate of 1 year per year. Age is a time varying variable. Work experience for people who are employed, the amount of work experience you have in your life changes at the rate of 1 year per year, at least if you're in the labor force continuously. So we're going to have to be careful about having, and we'll talk more about this later, but we're going to have to be careful about having like multiple counting variables. These are one way to think about time variables as counting variables. And so in this case, age is not a counting variable. It's a variable that means how old were you when the study started. Okay, so this is wide form data. This is wide form data. And the reason we know this is because we see, oh, look, time 1 suffixes, time 2 suffixes, time 3 suffixes, time 4 suffixes, time 5 suffixes. And then we have variables that don't change. ID doesn't change. Their age doesn't change. And whether they're Black doesn't change, at least in this study design. Okay, so now let's reshape it. Okay, how do we reshape it? Well, we can use PanelR. We're going to use the long panel function. We're going to use the long panel function. And this is really easy. This is really easy. We're going to create one called we're going to create a new data set called teen pov, which is going to be long form. We're going to do that by taking the original teen poverty data frame, and we're going to pipe it. Now, if some of you might not be, this isn't like a how to use R class, but I use a lot of piped workflows in R. And so this is what's called the native pipe. It's called the native pipe. Let me show you a quick example of this. We're going to take a break soon, but let me just show you a quick example of this. So here's like our studio. I got a bunch of stuff in the way here. So let me get a little R script, blank R script up. Now, if you do Control Shift M or Command Shift M, if you're in, whoops, if you're in Mac, it's going to make this little pipe. It's going to make this little pipe here. Now, you might be like, hey, wait, I've seen a pipe before, but it doesn't look like that. You can go to Tools, Global Options like this. And if you look at code, you're going to see right here in R, you have the option of using the native pipe operator or not. So you can say, I have this checked, use the native pipe operator. And this is only if you have R 4.1 or greater. Okay, it's only if you have R 4.1 or greater. So if I turn this off, watch what will happen. If I turn this off and then I say apply, which I can't see anything here, but I say apply and I close this out. Sorry, I'm working on my laptop and it's a little small. Okay, I'm going to close this out. Can I just say, eh. Oh, that's annoying. Okay. Come on, you can do it. Oh, all right. I made it big so you guys could see, but I'm getting in my own way. Okay, so we'll close that and I'll make it bigger again. Now, if I do Command Shift M or Control Shift M, you can see it makes this pipe, which might be one that you're familiar with. Now, I'm just going to tell you right now, if you are still typing, if you're still going like this, today is the day that stops. This is madness. Do not be typing 3 characters for this. Seriously, if you're using pipes and you're going like, just no, we're done. It's Command Shift M or Control Shift M on Windows. Just promise yourself. Do this for yourself. Practice. It makes your life better. Just practice. I'm telling you, you will thank yourself later. Okay. So either one is fine. Like in 99% of cases, not 100 unfortunately, but in 99% of cases, these two do the same exact thing. And so what do the pipes do? So let me show you. Well, I'm going to change it back to the native pipe because I prefer that. And this is what the pipe is. So if I said here, so here would be the traditional way. Again, many of you know this already, so my apologies to people who already know this. If I say, what's the mean of 1, 2, 3, 4, 5? Okay, if I want to know what the mean of that is. Oh, whoops. Oh, whoops. I don't, oh, sorry. What's the mean of this? You can see the mean is 3. Okay, make this a little bit bigger. Let's do this again. Okay, so the mean here is 3. All right, so that's just normal, but I could do this too. And I could do like that. That would also give me 3. Okay, so the pipe just says, hey, take this and send it to the next function. So take this thing and send it to the next function. So so I can do that. I could also do something like anyway, you could do something like this. You could do summary, LM, weight, or let me do miles per gallon as a function of weight, data equals MT cars like this. And that's going to give you like do a little linear regression for you and give you the summary. You want to see that. That's a little thing like that. Or you could do LM, MPG, weight, data equals MT cars, and then send that to the summary function. Now, the nice part about this, so I use pipe workflow a lot, is it's not shorter. I want you to understand it's not less typing. You know what I mean? It's not like it's shorter. I mean, you can see it's longer. It's longer in both cases, but it's just much more clear what's actually happening to use a pipe workflow. Like, hey, do this linear regression and then send the results to summary. So this is how I operate. This is how I operate. And from a speed perspective, now that the native pipe has been introduced, these are literally the same speed. There's no difference in speed whatsoever between these two now when you're using the native pipe. So anyway, you're going to see pipe workflows a lot in my stuff. And you can see this too. Like I'll just show you one more example. We'll just use the good old fashioned MT cars for this. Oh, whoops. I've got to do library tidyverse, sorry. Okay, so here's like the MT cars. And let's say, oh, I want to focus on just like cars with 8 cylinders. Okay, I could do this. I could do MT cars 8 is going to be take MT cars and then filter it so it only keeps sil equals 8. And you can see here that that is, you know, 14 observations instead of, however many that this is 32. So anyway, you get the idea. So this is like, you will see me use pipework rules all the time. Many of you will be already familiar with this. This isn't like my first course in R class. I mean, I'm happy to help people with R stuff where I can. But we presume a little bit of experience with R in this class, but that's the idea. So let me go back to the slides. We'll just finish this one slide and then we'll take a little bit of a break. So let's look at the so we have this data set already, this data frame already in memory, which is the one we saw before. This is teen poverty. I got this from the panel R package. So I got a data set called teen poverty, and I want to make a new version called teen pov, which is in long form. So what do? I take teen poverty, then I send it to the long panel function. And the long panel function says, hey, tell me what the ID variable is. Tell me the name of the variable you want for the new time variable that you're about to make. And tell me what's the starting period and what's the ending period. And so what this does now is it can look at this data set. You can look at this here and say, oh, okay. Okay, I see the suffix here is, 1, 2, 3, 4, 5. I know it starts at 1 and ends at 5. These variable ID is the ID variable. I told it that. Variables that don't have a 1, 2, 3, 4, 5 are time constant. So it's like smart. It can figure this out. And so what does it do? We made this new data set here, teen pov, and this is what it looks like. Well, we got, hey, what's your ID number? What time period is it? So we have person, so you can see here, we have person 22 5 times. 1, 2, 3, 4, 5. We have person 75. 1, 2, 3, 4, 5. Anyway, you can see that here. We have their age, and you can see this is again clear here. The age is not how old they are, because 16, 16, 16, 16, 16 is clearly not the person's age, but age here must mean age when the study started. Black, if they responded black, none of these respondents are black initially, but you can see like here's the poverty. So this person was in poverty at wave 1 and then not for the next 4. This person was in poverty only at the last wave. This person was in poverty the last 2 waves. This person was in poverty all but the first wave. Anyway, you can see how this works. Did they have a baby or not, et cetera. We're going to look at this data set a lot more, but I want to show you that this is really easy to use if you want to reshape your data from wide to long. And since you're probably not going to do this a million times, like at most you're going to do it once for a data set, I would recommend using long panel. It really is easier than dplyr, pivot longer. Not that pivot longer is very hard. It's fine. It's great. It's much better than like gather and spread, the old ways of doing it. But this is still easier. Okay.